So in this lecture our topic is analog Chebyshev low pass filter design. So in the last couple of lectures we talked about the Butterworth filter. We first talked about the motivation for analog filter design in a course on digital signal processing, and then we said we only discuss low pass filter because all other kinds of filter can be obtained by transformation of a low pass filter. And then we discussed the characteristics of Butterworth, and we said Butterworth is monotonic, right? So it is maximally flat, so maximally flat at omega equal to 0, and its asymptotic slope is 6n dB per octave, or we can say 20n dB per decade. Okay, and where this n, capital N, indicates the order of the filter, and this is true not only for Butterworth filter but also for any all pole low pass filter, all pole low pass filter or all pole transfer function. For example, we said if you have in the denominator s plus omega c, then continued product of a squared plus bk omega c plus omega c squared, where k equal to 1 to n minus 1 by 2, and in the numerator omega c to the power capital N. Okay, so then if omega c tends to infinity, all such transfer functions will have an asymptotic slope of 6n dB per octave. Okay, 6n decibels per octave. So it is nothing special about Butterworth. Okay, and then we discussed the pole locations. The pole locations were in a circle of radius capital omega c in the S plane, and the pole factors were either s plus omega c if the order is odd, or a continued product of a squared plus bk omega c plus omega c squared. And if capital N is odd, this is a transfer function. Okay, so the transfer function would be of the form omega c to the power n divided by s plus omega c multiplied by continued product of a squared plus bk omega c plus omega c squared, and the limits are k equal to 1 and n minus 1 by 2. In case if capital N is even, in this case continued product of a squared plus bk omega c plus omega c squared, k equal to 1 to n by 2, and in the numerator again once again omega c to the n. Okay, and in this expression you don't have to find anything else. Okay, in this expression or in this expression also, no need to find anything else other than only one guy, that guy is bk. And for this bk also we derived the formula. This bk is going to be 2 twice sine of 2k minus 1 times pi divided by 2n. Okay, and the range of k has already been specified, so there is no problem. So to design a Butterworth filter, all that you have to determine is omega c and capital N. If you have these two parameters, then you can design the Butterworth filter. But in general, okay, in general capital N will be determined from the given specifications. What are those specifications? Delta P, passband frequency omega P, and delta S, attenuation the stop band, and stop band frequency. So if you know these four parameters, from this you can find out capital N. Okay, so as I said, log 10 1 over delta S squared minus 1 divided by 1 over delta P squared minus 1, right, whole divided by twice log to the base 10 omega P divided by omega S, and this whole quantity must be greater than or equal to capital M. And this formula that you derived is very easy to prove. Okay, where capital N is greater than or equal to this quantity. Okay, for reasons to be made clear a little later, if you take this 2 in the numerator, then it will be 1 by 2 log to the base 10 1 over delta S squared minus 1 divided by 1 over delta P squared minus 1 whole divided by log to the base 10 omega P by omega S. And once again you can observe this 1 by 2 here by taking a square root sign. So log to the base 10 1 over delta S squared minus 1 divided by 1 over delta P square minus 1, I can put like this. Log to the base 10 omega P by, is it omega P by omega S or omega S by omega P? I am sorry. What did I do? I think I did a mistake. This is omega S by omega P, and omega S omega P, and here also omega S omega P. So this is the formula that we will use. Okay, so because reasons to be made clear a little later, this type of formulas we will use it. Okay, to let me call this N, capital N, and suffix P, where this B indicates Butterworth. Okay, we will refer to it later also. So it is the ratio of two logs, and one of them contains tolerances in the pass band and stop band. See, delta S is the tolerance in stop band, delta P is tolerance in pass band. Okay, in the numerator I have log of tolerances in the stop band and pass band, and in the denominator again I have the log ratio, but the ratio is between omega S and omega P. Okay, stop band and pass band edge ratio. So omega S is the stop band frequency and omega P is the pass band frequency. Okay, and then now let us consider an example. Okay, now let's say omega C is equal to 1000 pi radians per second, and omega S stop band frequency is equal to 2000 pi radians per second, and then attenuation the stop band delta S is greater than or equal to 40 dB. Okay, and attenuation the pass band is 3 dB. Okay, so This is okay and this is okay, but these two are in terms of dBs. Okay, so we need to convert into normal ratio. Okay, attenuation in the stop band is greater than or equal to 40 dB, and then from this which gives rise to delta S as equal to 10 to the minus 40 10 to the minus 40 divided by 20. So this is 10 to the minus 2 delta S. Okay, similarly delta P is equal to 10 to the minus 3, because the attenuations are in the negative, because the maximum value is 0 dB. If you recall the figure, this is the magnitude is normalized to 1. If you take this magnitude 1 in terms of dB, then the highest value is 0 dB. So 3 dB down, that means minus 3 dB. Okay, that is why I have taken here minus sign and here also minus sign. Minus 3 dB divided by 20. And if you find out this, then this is going to be 1 over root 2 delta P. So delta P squared is equal to 1 by 2. Okay, so we got delta S and delta P. So delta S squared is equal to 10 to the power of minus 4. Now you apply the formula, log to the base 10, then 1 by delta, what is the formula? 1 by delta S squared. So 1 by 10 to the minus 4 minus 1 divided by 1 divided by 1 by 2 minus 1 whole divided by log to the base 10 omega S by omega P, that is 2000 pi divided by 1000 pi. Now you simplify this, log to the base 10, then this is 10 power 4 minus 1 and 2 minus 1, it is 1, log to the base 10, this is 2. Now this right hand side calculates out to 6.64. okay, so this is NB is greater than or equal to the right hand side. So NB is greater than or equal to 6.64. The order of the Butterworth filter needed is, it should be an integer, right? So therefore it is 7. Okay, so with this obviously omega S realized would be lower than the specified. See, already omega S is 2000 pi. Now if you take 6.64, then this value is okay, but you are taking slightly higher than 6.64, therefore this omega S will be reduced to a new value. Okay, and here we don't have to find omega C. Omega C is already given. Okay, otherwise if omega C was not given, then what would we have done? First to find omega C. Okay, so why do you find omega C? What is the need? Because the transfer function is expressed, if you look at the transfer function, in terms of omega C. Okay, the transfer function is expressed in terms of omega C. Therefore we need to find out omega C and B case. These two are needed to write down the transfer function. Okay, therefore if NB is 7, obviously the realized omega S, that is the edge of the stop band, would be given by 1 divided by, you take the general formula, 1 divided by 1 by omega S prime divided by omega C to the power 2n. Okay, so I want to find out exactly where the stop band edge occurs. Okay, so that is why I have taken this omega S prime. Okay, therefore this whole quantity must be equal to how much? Delta S squared. Okay, and what is delta S squared? It is 10 to the power minus 4, and omega c is given 3 dB. Omega c is what? 3 dB frequency. Okay, that is given 1000 pi. So you can substitute that. So 1 divided by 1 plus omega s prime divided by 1000 pi to the power 2 times n, that is 14, right, is equal to 10 to the minus 4. And if you solve this, the omega s prime comes out 1930.6 pi. Okay, so it occurs earlier. So if you plot it, this is 1000 pi and this is, this is 2000 pi omega s. Okay, if you take NB is equal to 6.64, then this is the stop band and this is the pass band, which is equal to omega c, because it's a 3 dB frequency. This is 0 dB and minus 3 dB, no problem. But we did not take 6.64, we have taken 7. Because of slightly increasing the order, this omega s is shifted to the left, this value, and this value let me call omega s prime, and this is going to be 1930.6 pi. And this is a welcome feature. Okay, so you are moving the stop band slightly to the left hand side, that means your filter is good, so one should be happy about it. Okay, one should be happy about it that you have satisfied the stop band. In fact, you have over satisfied the stop band. And in addition, now you can find out the transfer function HA of s, that would be in the numerator omega c. If you recall the general formula, I have written here, if it is odd, this is for even, right? If it is odd, this is a formula, omega c to the power capital N divided by s plus omega c, and this is a formula. The same thing we are going to apply here. So in the numerator, omega c to the power 7, and then you have one first order factor because the order is odd, and then multiplied by k equal to 1 to 7 minus 1 by 2, that is 3. A squared plus bk omega cs plus omega c squared. Now expand this. This is s plus omega c, then multiplied by a squared plus b1 omega cs plus a squared, multiplied by a square plus b2 omega cs plus a squared, multiplied by a squared plus b3 omega c s plus omega c squared. In the numerator, omega c to the power 7. Okay, so what is omega c? Omega c is 1000 pi, and you have to find out the constants. Okay, so b1, b2 and b3. Okay, so we know the formula, right? What is the formula? bk is equal to twice sine of 2k minus 1 pi by 2n. Here n equal to 7 and k ranges from 1, 2 and 3. So b1 is equal to twice sine of k equal to 1 means 2 minus 1, 1 pi divided by 2 times 7, 14, pi by 14. Okay, so while calculating this b case, don't forget this factor 2. Okay, so sometimes people will forget this. Okay, 2 we should not forget. Then b2 would be twice sine of, again no need to go to this formula. Okay, directly you can write. So from this you add plus 2 pi in the numerator. Okay, so therefore this is going to be pi plus 2 pi, this one pi. I'm telling you add 2 pi in the numerator in the argument of sign. Therefore this is 3 pi by 14. So don't go to this formula every time. Once you have written this b1, then automatically you can write down b2, b3, b4 by adding 2 pi in the numerator of the argument. And then b3 is equal to twice sine of, again add plus 2 pi in the numerator, so 5 pi by 14. Okay, so after a while you will lose contact with who is Butterworth and what is the filter and so on. So you would be able to do it almost blindly, and it will be very easily programmed. Therefore, given the order capital N and the cutoff frequency omega c, you can always find the transfer function. Okay, so that's about Butterworth. Now let us go to Chebyshev. Okay, so Chebyshev filter. So let me say Chebyshev low pass filter, LPF. The spelling of Chebyshev is quite complicated, and this is the American spelling. Okay, actual spelling is TSCHEBYSCHEFF. Okay, well, we will use the American spelling, and most of the authors they use American spelling. Okay, Chebyshev low pass filter has the distinctive characteristic that if elliptical filters are excluded, then Chebyshev low pass filter is the optimum one. Okay, if elliptic filter is excluded. Okay, optimum one always is the elliptic filter. If the elliptic filter is excluded, because elliptic filters are complicated to design, then Chebyshev low pass filter is almost always preferred. Therefore, the Chebyshev filter is the optimum if we exclude elliptic. But if we include elliptic, then this elliptic filter is the optimum filter. Optimum means for a given capital N, delta P passband attenuation and stopband attenuation for a given order and the same tolerance, the Chebyshev low pass filter of all pole filters that are possible will give the narrowest transition width. So that's what we mean by optimum. Okay, if any filter which has narrowest transition width, then we say that filter is the good one. Okay, so you have to design a filter such that the transition band should be as low as possible. If you take ideal filter, what is the transition band? If let's say this is my low pass filter, this is my low pass filter and this is omega p. Now this is my stop band. Okay, now the transition band is 0 here, transition width equal to 0. So if you reduce the transition width as low as possible, then your filter is very good, the best one. Okay, now if you look at here in this ideal filter, say this is my pass band, up to here pass band, and then suddenly it becomes 0. So the transition width is very less. In fact, it is 0. Okay, but that is not possible in reality. This is ideal. Okay, in practical we can't design a filter with a transition width of 0. Therefore, the elliptic, if you design a filter using this elliptic method, then the transition width is reduced. But again, no, there are certain complexity. so we can't use elliptic filter. So that's why people will prefer to use Chebyshev filter. So if you exclude the elliptic filter, then the Chebyshev low pass filter gives the narrowest transition band. Okay, so it can also be specified or it can also be qualified or characterized in alternative ways. For example, the Chebyshev filter is characterized by specifying capital N and transition band. Okay, generally the customer will give you this kind of specifications, okay, and then they will tell you how much the tolerance in the pass band, and then delta S. Okay, delta P are specified, it will give you the lowest delta S. Our aim is we have to design lowest delta S. These three are given. Capital N is given, transition band is given, and delta P is given. With this, if you design a low pass filter using Chebyshev method, and that will give you the lowest value of delta S. Okay, you design a filter for a given specification such that if you minimize delta S as possible as, then your filter is very, very good. Okay, so it is a combination of them, but the amount of delta S that you reduce, then it is good. Now, as we said in the Butterworth, where the characteristic is monotonic, okay, but here the characteristic has ripples in the pass band instead of monotonicity as in the Butterworth filter. Okay, this is 1 and this is delta P. Now there will be some oscillations in the, oh my god, omega is like this. So ripples in the pass band, and this one is stop band, and monotonicity in the stop band. Okay, so the characteristic ripples in the pass band. Okay, therefore I'm sorry, this is wrong actually, it should touch the up, top and bottom like this. Okay, so that is the characteristic is something like this. Okay, and this is 1 and this is delta P, and this is delta S, this point is omega P, and this point is omega S. Okay, so it ripples in the pass band like this, something like this. Okay, see, I am intentionally not showing at omega equal to 0. Okay, here I did not complete the figure, so that we will see a little later, because it differs according to the evenness or oddness of the transfer function. Okay, so it executes equal ripples in the pass band, and it is monotonic in the stop band. So unlike Butterworth, it is not a monotonic filter. It has maxima and minima between the two limits. The maxima reach equal amplitudes, the minima reach equal amplitudes. So it has equal ripple in the pass band. Okay, equal ripple is sometimes abbreviated as equiripple. So it has equiripple in the pass band and monotonicity in the stop band. There can also be another type of Chebyshev. We can reverse the order. Okay, we can reverse the role. So in the pass band monotonicity like this, and in the stop band there is a ripple. Okay, so we can have monotonic in the pass band and equal ripple in the stop band, and this is called a type 2 filter, type 2 Chebyshev low pass filter, and this one is called a type 1 low pass filter. Okay, so type 1, type 2. In type 1 equal ripple or equal ripple, whatever it is, equal ripple in the pass band and monotonic in the stop band. In type 2, monotonic in the pass band and equal ripple in the stop band. Okay, and this type 2 is called inverse Chebyshev filter. Okay, now obviously type 1 is the preferred filter. Why? Because a stop band is stop band. We don't care whether it is ripple, whether it has ripple or monotonicity or whatever there in the stop band. Okay, once we have specified a delta S, and once we have satisfied this delta S, one should not bother whether there are ripples or not in the stop band. Therefore, we will discuss only type 1 filter. Type 1 is the most favored optimum low pass filter, provided you exclude elliptic filters from your field of view. Okay. So let me stop here. We will continue from this point in the next lecture. Okay, in the next lecture we will discuss the transfer function of the Chebyshev filter, I mean magnitude function of a Chebyshev filter, and then Chebyshev polynomial and so on. Okay, thank you very much.